بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this video we will introduce spherical coordinates, which is a new type or a new way to represent points in space. We are of course familiar with representing a point with rectangular coordinates x, y, z. This is the rectangular way. In fact, we can also represent this point by another type of coordinates, or by three numbers, okay? Three different numbers, which we call spherical coordinates. So what are the spherical coordinates that can be used to represent a point in space? So if we take just any point, arbitrary point p, x, y, z, so just let's take it here, arbitrary point p, x, y, z, the rectangular coordinates are x, y, and z. We can represent this point also by three other numbers p, and these numbers are called rho and theta and phi. Three new numbers. What are these three new numbers? What is rho? What is rho? Rho is the distance from the origin to the point p. So this is rho. So rho, the distance from the origin to the point. So this is the number rho, the first coordinate. And since rho is a distance, then rho has to be greater than or equal to 0, since it is a distance. This is the first number. The third number, phi, it is the angle between the positive z-axis and the line segment OP. So this is phi. So phi, the angle between the positive z-axis and the line segment segment OP, between the z-axis, the positive z-axis, to the line segment OP. And phi, the restriction of phi is the following. It is really between 0 and pi. And this will be shown, this will be clarified further very soon. So this is the angle phi, the last number. Now the second, the middle number, theta, it comes really from the polar coordinates. So here, take the point p, x, y, z, and take the projection of the point in the xy plane. So this is x, y, and 0. When you take the projection of the point in the xy plane. Now in the xy plane, find the polar coordinates of the points here. So here you have, for the xy plane, you have theta. This is theta, and r is the distance from O to the projection. Okay, so this is r. So theta is the angle that comes from the polar coordinates. The polar coordinates are theta. So theta, it is the angle corresponding to the point, the polar angle corresponding to the point xy. We take just xy because the z component is 0 in the xy. And it is restricted between 0 and 2. We take this restriction. So these are the three new numbers, rho, theta, and phi. And they are called the spherical coordinates of the point. So this is how to define a new description of the same point in space. We can use either rectangular, the usual way, the familiar way, or the new way, which is the spherical coordinates that consists of the three numbers rho, theta, and phi, as defined. Now, as usual, it is nice to find a relation between the rectangular coordinates of the point and the spherical coordinates. So let's see how to find the relation between the two coordinates. And from the graph here, we can really find the relation between them. So just let's take first some basic relations from the graph. So this is R, and this is also R. So they are parallel, and this is rho, and this is the angle phi, and this is, of course, from here to here, this is Z, and from here to here, this is Z. So from here to here, it is Z, and this is X, and this is Y. If we concentrate on this rectangle, a right angle rectangle here, notice what is Z here? Cosine phi equals rho of Z over rho. So this is cosine phi. This implies then Z equals rho cosine phi. So cosine phi equals Z over rho. Then Z equals rho times cosine phi. Sine phi R over rho. So really get R equals rho sine phi sine. So these are the first two relations. So here Z equals rho cosine phi and R equals rho sine phi. And of course, when you go to the polar coordinate, to the xy plane, the relation between xy and r theta are the polar relations. So we have also x equals r cosine theta and y equals r sine theta. So these are the relations, some basic relations from the graph. Okay. Now the relation between rectangular to spherical. Rectangular to spherical. These are the major one are the fun one. Now what is the, if you want, we have, what is the x in terms of the spherical coordinates? X equals r cosine theta and r equals rho sine phi. So x equals rho sine phi cosine theta. What about y? Y equals r sine theta, but r is rho sine phi. So y equals rho sine phi sine theta, So this is x in terms of the spherical coordinates, y in terms of the spherical coordinates. What about z? Z equals rho cosine phi, rho cosine. So these three relations gives us, well, if you know the spherical coordinates, I can find the rectangular coordinates. Okay. We have one more relation, which is this follows from the definition of rho. Rho is the distance from the origin to the point x, y, z. What is the distance in that case? Rho equals x squared plus y squared plus z squared under the root. If you square the root, I get rho squared. So just finding the distance from the origin to the point x, y, z, I get it rho. When you square, you get rid of the. But this is the fourth relation. In fact, these four relations help us go from really spherical to rectangular. And these are the basic relations between them. But also, in many occasions we have also to go back to the first 4 basic ones, especially the second one, r equals rho sine phi. So these are some the basic relations that help us go from rectangular to spherical. Now we consider basic graphs in spherical coordinates. So we have the point with spherical coordinates rho, theta and phi. The basic graphs that we will consider are when one of each of these coordinates equals a constant. So we start with rho. If rho equals a, where a is positive, because rho has to be greater than or equal to 0, so we start with a positive number. If rho equals a positive number, so what is the graph of this equation in spherical coordinates? And for example, if rho equals 1, what is the graph of this equation? Or rho equals 2, what is the graph of this equation? A simple way to find the graph of this equation is really just to change it to rectangular. Okay. So here the relation between rho and the rectangular x squared plus y squared plus z squared. If rho equals 1, then I get 1 equals x squared plus y squared plus z squared. So using this relation, I get really 1 equals x squared plus y squared plus z squared. The same thing for 2. If I use rho equals 2, I get 4 equals x squared plus y squared plus z squared. So what is the graph of these equations? It is obvious. This is really the r spheres with center the origin and radius here 1 and radius here is 2. So if rho equals a specific number, any positive number, the graph of that equation will be a sphere. So here a sphere with center, the origin and radius equals a. So rho equals a. The graph is a sphere with center the origin and radius a. So this is if a is positive. What about if rho equals 0? If a equal to 0, so rho equal to 0. What is the graph of this equation? Well, again, you can use the same thing. If rho equal to 0, then I have 0 equals x squared plus y squared plus z squared. And this is just a point, just the origin, the origin. Notice here you are adding positive numbers. If you are adding positive numbers and you get 0, then each one of these numbers has to be 0. Or geometrically, rho is the distance from the origin to the point B. If the distance from the origin to the point B is 0, then B has to be the origin. Here, rho equal to 0, it is just the origin. So this is when rho equals a constant. Now we go to the last coordinate phi. Here, and we remember phi is the angle between the positive z-axis and the line segment OP. This is the angle. So if phi equals, let's say phi now, this is the second part, phi. Let me start with phi equal to 0. What is the graph of this equation? i.e., what are the points whose phi equal to 0? What are the points in a 3 space whose phi, the angle phi, equal to 0? From the definition of the angle phi, it is the angle between the positive z-axis and the line segment OP. So this is the z-axis and you just move an angle of phi. Now here, if I did not move phi equal to 0, then I will be where? Well, I will be just on the positive z-axis. So this is phi equal to 0. There is no move, there is no rotation. So if phi equal to 0, then I will consider only all points on the positive z-axis. All points on the positive z-axis, phi equal to 0. So phi equal to 0, this becomes the positive z axis. Now, let me take phi equals pi over 2. Phi equals pi over 2. What are the points in space whose angle phi equals pi over 2? So, starting measuring the angle phi from the positive z-axis, I have to move an angle of pi over 2. An angle of pi over 2. Of course, in all directions. In all directions. So, I will get what? I will get the xy plane. XY plane. This is the positive z-axis. Now, we move an angle of pi over 2. This is pi over 2. This is pi over 2. This is pi over 2. And this is pi over 2. In all directions. In all directions. Then you will get the points in the xy plane. So here phi equals pi over 2, the xy plane, the xy plane. What about phi equals pi? Phi equals pi. So now you measure, you find the points whose angle phi equals pi. Again, you move from the positive z-axis, an angle of pi. Here the positive z-axis. Rotate an angle of pi. We'll get the negative z-axis. Okay. And you go in all direction, any direction. Always you will reach the negative z-axis. So this is the negative z-axis. Now, negative z-axis. Now take angle between 0 and pi over 2. This is take phi equals phi 0, and this is between 0 and pi over 2. So take phi between 0 and pi over 2. But what are the points? What are the points whose angle will be phi 0? And for example, if I take phi equals pi over 4. What is the graph of this equation? What is the collection of all points in space whose phi equals pi over 4? Again, it is very simple by rotation. This is the positive z-axis, and you measure phi by rotation, by moving. Okay. So now I have to move the z-axis or rotate it an angle of pi over 4. Well, if I rotate this z-axis an angle of pi over 4, I get another line. All of these lines will making an angle of pi over 4. So here, let me just write it in this manner here. So this is, if I rotate pi over 4. So this is a line, okay. So in one direction. But I have to go in all directions. In all directions. So in this pi over 4, you go pi over 4, you go pi over 4, you go pi over 4 in all directions. In all directions. In that case, you get different lines. Another line, and etc. Line coming here, line coming there. You will end up with ايش? Will end up with a cone. With a cone. This is ايش? A cone. Just a line, you rotate it pi over 4 in all directions. In all directions. You get a cone. Or let's say an upper cone, an upper cone. So here an upper cone, an upper cone with axis, the z-axis there, z-axis, and vertex, the origin. So this is if the angle phi between 0 and pi over 2. We get a cone, an upper cone. What about if phi equals phi 0, but now phi 0 between pi over 2 and pi. Between pi over 2 and pi. For example, if you take phi equals 3 pi over 4. So what is the graph? What are the points in space whose phi equals 3 pi over 4? Again, you start with the positive z-axis and you rotate 3 pi over 4 in all directions. So this is pi over 2, this is 3 pi over 4. Okay, so this is just one possible line, so this is 3 pi over. This is one possible line. This is 3 pi over 4. 3 pi over 4, but you take it in all directions, and then you will get really a cone, okay? A lower cone. In this case, a lower cone with axis, the z-axis, and vertex, again, vertex is the origin. So if phi between 0 and pi over 2, I get an upper cone. If phi 0 between pi over 2 and pi, I get a lower cone, okay, with axis, the z-axis, and vertex, the origin. What about if phi greater than pi? Is it possible or not? So we take pi greater than, just here. Okay. Is it allowed or not? If you take phi greater than pi, so this is pi, and then you come here. But if you go further, well, I can go in the direction. So here phi is less than pi. So really this is not allowed. If it is larger than pi, it is not allowed. There is no need, because you can just measure it in the other direction. Because we are measuring phi from the positive z-axis, and we go in any direction we want, Okay. So in that case, we can go up to phi equals pi. No need to go larger than pi. So this is why the possible values of phi are from 0 to 2 pi. This is for phi. The last one now, the basic graph, when the middle theta equals an angle. The angle theta equals theta 0. And here, since theta comes from polar coordinates, so the definition or the graph comes again from polar coordinates. If you take theta equals theta 0 in polar coordinates, okay, you just measure theta from the positive x-axis, so you go just in the xy plane, in the polar. The graph of theta equals theta 0 is just array. So this is theta 0. It is array passing through the origin. And here we ignore r because we don't have really r in spherical coordinates. We have really half array. We don't have a full array. There is no r here in spherical coordinates. But it is half array, a line passing through the origin. This is the graph in the xy plane, but we need the graph in space. So the missing variables phi and rho or z. In that case, we just translate along the missing variable. Okay. So here we get when you translate this line, you get a plane. Half a plane or a door hinged on the positive x-axis. So this is half a plane, attached to the z-axis, making an angle of theta 0 with the positive x-axis, with the positive z-axis. This is the graph of theta equals theta 0. And of course, it goes up and down, okay, along the full z-axis, along the full z-axis. So you go making the positive x-axis, So these are the basic graphs that we need really to do triple integration later on when in spherical coordinates. We consider now the following problem. A point P has the rectangular coordinates -5, -3, 5, and 0. Find its spherical coordinates. So we have the rectangular coordinates and we need to find the spherical coordinates. So here we have, from the given information, we have x equals -5 √3 and y equals 5 and z equals 0. And we need to find the spherical coordinates rho, theta, and phi. Rho, theta, and phi. And to find the spherical coordinate, we use the identities, we use the relations that connecting rectangular and spherical. So if I know x, y, and z, how can I find rho? Well, this is very simple. We have the relation rho squared equals x squared plus y squared plus z squared. I have this relation. So if I know x, y, and z, I can find rho. This gives us the following. This is rho squared. X squared, this is 25 times 3, 75, 75, plus y squared, which is 25, plus z squared equals 0, and this is 100. Okay. So this gives us rho equals 10. Why? Because rho is greater than or equal to 0. So the value of rho is 10. Now the next one, I can find the phi. Again, I have to use one of the relations, and the relations then we have z equals rho cosine phi. So if I have rho, yes, and I know z, it is given. If I know z and rho, I can find phi. Okay. So substitute. This gives us this is z equal to 0 and rho equals 10 cosine phi, and this gives us cosine phi equal to 0, and hence phi equals pi over 2. Again, since phi between 0 and pi over 2, between 0 and pi. So phi, the angle whose cosine is 0 in this range is pi over 2. So this is phi. For theta, well, I have the x and y, so I can use either one of them. So let me choose y. So this is y equals rho sine phi sine theta. Well, I know y and I know rho and I know phi. Well, I can find theta. So this is h reduces to one equation in one unknown. So substitute to get theta. Y equals 5. Rho equals 10. This is 10. Sine phi is pi over 2. Sine theta. This gives us sine theta. Sine pi over 2 is 1. Then 5 over 10. This is half. Well, so I need the angle theta whose sine is equals half. So theta equals either pi over 6 or 5 pi over 6. Again, theta between 0 and 2 pi. And in this range, these are the two possible values. Now, I cannot, of course, take two values. If I take two values, I will get 2 points. If I take the two values, I will get 2 points. But corresponding to this point, I should have only 1 point with spherical coordinates. So I have to decide which angle should I choose, pi over 6 or 5 pi over 6. To decide that, I have to go to the point in rectangular coordinates and just try to locate this point. If you locate this point here, so this is x, and this is y, and this is z. So it is x is minus 5 root 3, so this is x minus 5 root 3, so this is the point here, it is negative, and y equals 5, and this is y equals 5, and z equal to 0. So it is a point in the xy plane, The point is in the xy plane, and it is in the second quadrant, second quadrant of the xy plane, Now the angle theta comes from polar coordinates, and here theta either pi over 6 or 5 pi over 6. So it is in the plane, in the xy plane. Now if the point is in the second quadrant, then the angle theta will be what? It will not be pi over 6, it will be 5 pi over 6, 5 pi over 6. Since the point, or the projection of the point, which is the same in this case, it is in the second quadrant. So in the second quadrant, theta has to be 5 pi over 6. So this is H, imply theta equals 5 pi over 6. So now, rho theta, and phi, the spherical coordinates of the given point are 10, theta 5 pi over 6, and pi of phi equals pi over 2. So these are the spherical coordinates of the given point. We consider the following problem. Convert the equation z equals root x squared plus y squared to an equation in spherical coordinates. So we are given an equation in rectangular coordinates. We want to find the corresponding equation in spherical coordinates. So how to change it to an equation in spherical coordinates? Here the situation is very simple. Just you need to replace z, x, y by their corresponding values in spherical coordinates. So just write there. So this is z equals root x squared plus y squared. Replace each variable by the corresponding relation in spherical coordinates. So z in spherical coordinates equals rho cosine phi, root x in spherical coordinates equals rho sine phi, sine theta. When you square, so this is squared, and this is squared, and this is squared. Plus y squared. Sorry, here this is cosine theta. Plus y in spherical coordinate, it is also rho sine phi, sine theta. When you square, you get square and square. So just replace each one of the variables by their corresponding values in spherical coordinates. Next, you have to simplify. Just simplify your works. Okay, so this is root. Inside the root, notice that rho squared and sine squared phi is a common factor. This is rho squared, sine squared phi. What remains? Cosine squared theta plus sine squared theta. But cosine squared theta plus sine squared theta equals 1. So this becomes just root rho squared sine squared phi. We'll take the square root. The square root of this gives us absolute value of rho sine phi. Absolute value. But we know that rho is positive, greater than or equal to 0. So it will come out, absolute value of rho will be rho. But also sine phi is positive because phi between 0 and pi. Okay. And the sine of phi in this case is also greater than or equal to 0. So it comes out as sine phi. So the absolute value for rho sine phi equals rho sine phi. So I have rho cosine phi equals rho sine phi. This gives us the following. Just if I can simplify further. Take this term to the other side. I get rho cosine phi minus rho sine phi equal to 0. And this gives us rho times cosine phi minus sine phi equal to 0. And this gives us either rho equal to 0 or cosine phi equals sine phi. So I have two equations now. I have two equations. Rho equal to 0 or cosine phi equals sine phi. Or should I choose both of them or one of them? If you look at rho equal to 0, what is the graph of this equation? This is just the origin. The origin. So the graph of this equation is just the origin. Well, but the given equation is really not an origin. It is a cone, an upper cone. Z equals root x squared plus y squared. It is not a point. It is a cone. So this is rejected. Because this does not represent really the equation of the given cone. Okay, so this is out. Then cosine phi equals sine phi. This gives us phi equals pi over 4. Because phi between 0 and pi. So the only angle whose cosine equals its sine is the angle phi equals pi over 4. So the equation this in spherical coordinate or the spherical equation is phi pi over 4. Okay. It is the equation corresponding to the equation of the given rectangular equation. It is a cone. Yes, and also based on our knowledge of the basic graphs, the graph of phi equals pi over 4, it is also an upper cone. Okay. So we end up with the required equation is phi equals pi over 4. Okay. So this is the answer. Let's consider the following problem. Describe the graph of the spherical equation rho sine squared phi equals cosine phi. We need to describe the graph of this equation or just graph this equation. Here for the solution, of course, this is not a basic graph or this is not a basic equation. So really it is not easy to find or to describe its graph. So in this case, if it is not a basic equation or a basic graph, it is better to change the given equation to rectangular coordinates. Change it to rectangular coordinates because we are all familiar more with the rectangular with equations given in rectangular coordinates. So it is better to change to rectangular coordinates. Change to rectangular coordinates. So I have rho sine squared phi cosine phi. How to change it to rectangular coordinates? Here you have just to recall the basic equations, the connecting equations between rectangular and spherical. And one of the equations is really z equals rho cosine phi. This is one of the equations. So in that case, and I have cosine phi, and to get z, I need rho. So just multiply both sides by rho. So you have rho sine squared phi equals cosine phi. Multiply both sides by rho, you get rho squared sine squared phi equals rho cosine phi. This gives us the following. So rho cosine phi equals z. What about rho squared sine squared? This is, you have to recall the basic graph. The basic graph connecting spherical and rectangular coordinates. We have also this r equals rho sine phi. So really this is ايش r squared. R that comes from the polar. You need to recall the basic graph connecting rectangular and spherical coordinates. So this is rho r squared. But what is r squared? This is just x squared plus y squared equals z. So the rectangular coordinate, the equation in rectangular coordinates corresponding to the given spherical equation is this one. Now the graph is a paraboloid, and with vertex the origin and axis the positive x-axis. This is the graph. So the graph of the given spherical equation is just a paraboloid. We consider now the following problem. Find a spherical equation corresponding to the rectangular equation x squared plus 2x plus y squared plus z squared equal to 0. So here we need to change this equation to an equation in spherical coordinates. And as usual, this is not difficult, just replace x, y, z by their corresponding equations or relations in spherical coordinates. So here I have, I can just reorder, so we have x squared, so this gives us, this is x squared plus y squared plus z squared plus 2x equal to 0. Change to spherical coordinates. I know that these three terms, x squared plus y squared plus z squared equals rho squared. So this is rho squared plus 2. What is x in spherical coordinates? It is rho sine phi cosine theta equal to 0. Simplify further, I can take rho as a common factor. So this is rho times rho plus 2 sine phi cosine theta equal to 0. And then I have the following, either rho equal 0 or rho equals minus 2 sine phi cosine theta. Which equation should I choose? Of course, the graph of this equation is just a point, the origin, point O, the origin. And the graph of the given equation is really a sphere, not a point. Okay. It's very simple to show that it is a sphere. Just complete the square in x. You add 1 and you add 1. You get a sphere with radius 1, center minus 1, 0 and 0. So it is not a point. So this is rejected. So the solution is just this equation. So this is the required equation. So the spherical equation corresponding to this sphere is given by this equation. Rho equals minus 2 sine phi cosine theta. Bismillahir Rahmanir Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss triple integrals in spherical coordinates. The situation really is similar to triple integrals in rectangular and in cylindrical coordinates with minor changes, but the main idea is the same and probably similar. Okay, so let's just start with what we have. So here in spherical coordinates, the function will be a function of rho, theta and phi. So let's assume that this function is continuous in the following solid in 3 space. The set D consists of the set of points rho, theta, phi with the following description. Rho between two curves, G1, theta, phi, G2, theta, phi. So here rho will be a function of theta and phi. theta and phi, between two surfaces, or in terms of theta and phi. The angle theta between A and B, and the angle phi between C and D. So this is really the type of solids that we will consider when we deal with the triple integrals in spherical coordinates. So it is just one type, one type. Okay. Now, if you want to find the triple integral of a function over D, here to set up the limits of integration on this set D, we have the following. This is the function f is a function of three variables, f of rho, theta, and phi, and dv. Here dv in spherical coordinates has the following value. This is equals rho squared sine phi times the d rho d theta dv. So this is dv, this is dv. So we have for dv a factor of rho squared sine phi, which is really similar to the factor in polar coordinates. You have r dr d theta on cylindrical coordinates, r dz dr d theta. And it comes from really taking a solid in 3 space described in spherical coordinates and then dividing it and finding the volume of a spherical rectangle. Okay. The volume of the spherical rectangle will be given by this quantity. So this is the origin of this factor. But we will always have one order, which is we start with d rho, then d theta, and then d phi. So here it becomes easier, at least from this regard, where you have only one order. Now, what are the limits? What are the limits of these rho, theta, and theta? Well, the inner will go with rho as usual. So the limits of rho are g1 and g2. So this is g1 of theta phi to g2 theta and phi. Then theta goes from A to B, theta, the middle integral, A to B. Then phi, the last differential, goes with the last integral. The limits are C to D. Then we integrate in the usual way, starting with the innermost, then the middle, then the outer. So this is how to set up the limits of integration. Basically, the main point in the following example that we have to concentrate on is how really to set up or how to describe the solid in spherical coordinates. Once we specified or described the solid in spherical coordinates, specified the limits of rho, theta, and phi, then setting up the limits of integration is not difficult. It becomes very, very simple. And then integration, again, it becomes very, very simple. So really the main point here is how to describe the solid in spherical coordinates. And this is what we will do next. We'll illustrate this with the following example. To illustrate the triple integrals in spherical coordinates, we consider the following example. Find the volume of the solid inside the sphere, rho equals 2, and between the cones, phi equals pi over 6 and phi equals pi over 3. So it is a volume problem, so the solution as usual, solution. The volume is triple integral of 1 dv over the solid D, So the volume formula is true whether it is in rectangular or cylindrical or spherical coordinates. So this is the formula for the volume. The next step is to set up the limits of integration. Okay. And for that, we need to describe the set D in spherical coordinates. So how to set up this, how to describe D, the solid D in the spherical coordinates, we try to sketch the solid, and then from the graph it will become very easy to describe the solid in spherical coordinates. So now we graph these solids. We have a sphere, a solid inside the sphere rho equals 2. So we have a sphere rho equals 2. So the center is the origin and the radius is 2. So this is the sphere. And between the cones, phi equals pi over 6 and phi equals pi over 3. So you take an angle of pi over 3 from the positive z-axis, pi over 6. So this is the first cone. This is the inner cone, pi over 6. And then you take another angle from the positive z-axis, pi over 3, to get the second cone. So you have a cone inside another cone. The solid will be inside the sphere and between the cones, the two cones. So the solid will be the part between the two cones. Be this part here. And this part. Of course, around, it will go around. So, but it is between the two cones and inside the sphere. Okay. So this is the solid. Okay. This is the solid that we want to find its volume or its description in spherical coordinates. So to describe D is the set of all rho, theta, and phi. What are the limits of rho? What are the limits of rho? How to measure the limits of rho? For rho, to measure rho or to find the limits of rho is a distance from the origin. So we have to start. We take a ray from the origin. If you take any ray from the origin, if you start with a ray inside the origin here, just enter the solid. Okay, enter the solid. Of course, you are already in the solid. So you are entering the solid really from the origin. You are entering the solid from the origin. Since we are entering from the origin, then the lower part or the lower limit of rho is 0. So you start off with the array from the origin, you enter the solid. Well, 0 is already in the solid, so I start with rho. And then continue. Then I leave the solid at rho equals 2. I enter from the origin and I leave through 2. So the upper will be 2. So this is how to decide the limits of rho. Okay. Really, it is similar to deciding the limits of R in polar coordinates. In polar coordinates, we start from array from the origin through the solid. The same thing here. Okay. You start with the array from the origin and enter the solid. Where you enter the solid is the lower, and where you leave is the upper. So I enter the solid from 0, the origin, and I leave at rho equals 2. So this is my outer. So this is how to set up the limits of rho. Now the next part, theta and phi. So I will start with phi first. Start with phi. Phi is the angle that we measure from the positive z-axis. Okay. So what are the possible angles inside the solid? Well, if I start from the positive x-axis and rotate, I will reach pi over 6. When I reach pi over 6 still, I am not in the solid. But starting with pi over 6, well, I will be in the solid. So when you just rotate from the positive z-axis, you will start entering the solid at pi over 6. And if you continue, you will leave at pi over 3. So the possible values of phi are pi over 6 to pi over 3. So this is pi over 6 to pi over 3. These are the possible angles of phi inside the solid. What are the possible values of theta or the limits of theta? Here the theta is measured from the positive z-axis, and you are rotating inside the xy plane. This is the measure of theta. So theta is just like the measure of theta in polar coordinates. Inside our solid, it is the region between the two cones. So it is just like a circular part. If you take any point in the solid, the theta will be from 0 to 2 pi. I will cover all possible theta. So it is a rotation around the z-axis. Here all possible values of theta. If you take the projection of the solid, it will be a circle. Or if you take any point here, just rotate around the positive z-axis, from the positive x-axis and rotate, you will cover all possible values of theta. I will take a rotation around the positive z-axis. So theta will be from 0 to 2 pi. So these are the limits. Now once we know the limit, now just substitute here. So the volume will be triple integral of 1 dv. The dv factor is rho squared sine phi. The order is d rho, then d theta, then d phi. And the limits for rho 0 to 2, the middle theta 0 to 2 pi, and the outer phi pi over 6 to pi over 3. So this is the setup of the limits. Now we integrate from the outer, then the middle, then from the inner, then the middle, then the outer. When you integrate, first start with the innermost. When you integrate with respect to rho, sine phi is a constant, and integral of rho squared 1 over 3 rho cubed, from rho equal to 0 to rho equals 3. And this becomes pi over 6 to pi over 3, 0 to 2 pi. This is sine phi, When you substitute, this is 2. When you substitute, you get 8 over 3. 8 over 3. D theta, d phi. The next one is the integral with respect to theta, and this is a constant with respect to theta. So this is pi over 6 to pi over 3, 8 over 3 sine phi. When you integrate with respect to theta, I get just theta, from theta equals 0 to theta equals 2 pi d phi. And here, when we integrate, we get the following. And this is 2 pi times 8 over 3, 16 pi. So this is pi over 6, 2 pi over 3, 16 pi over 3 sine phi d phi. Now we integrate with respect to phi. So this becomes 16 pi over 3. This is a constant. Integral of sine minus cosine phi, from phi equals pi over 6 to phi equals pi over 3. And this is minus 16 pi over 3. So cosine pi over 3 minus cosine pi over 6. With a simple triangle, just the usual triangle here, 1, 2, root 3. So this is pi over 6, and this is pi over 3. This is minus 16 pi over 3. Cosine pi over 3, it is half, minus cosine pi over 6, root 3 over 2. And this is 8 pi over 3, root 3 minus 1. So this is the volume of this problem. We consider the following problem. Use spherical coordinates to find the volume of the solid that lies within the sphere x squared plus y squared plus z squared equals 4, above the xy plane and below the cone z equals root x squared plus y squared. So it is a volume problem of a solid. So the formula is just volume triple integral of 1 dV over the solid du. So this is the general formula. Here we need to find the volume using spherical coordinates. So we have to really first sketch the solid and then describe it in spherical coordinates. So we have the sphere x squared plus y squared, x squared plus y squared plus z squared equals 4. It is a sphere of center, the origin and radius 2. In spherical coordinates, this is rho squared equals 4 and hence rho equals 2. Since rho greater than or equal to 0. So rho greater than or equal to 0. And we have also to describe the cone in spherical coordinates. So this is the cone z equals root x squared plus y squared. In fact, when you substitute z, which is rho cosine phi, and the value of x and the value of y in spherical coordinates, and you simplify with some work, you will get you will get phi equals pi over 4. So we leave this for you to do. So now the solid is inside the sphere, rho equals to below the cone, pi over 4, and above the xy plane. Okay. Let's sketch this solid. So here I have a sphere of radius 2. The solid is above the xy plane, so it is enough just to consider the upper part of the sphere. The solid is above the xy plane, so I will take half the sphere, the half of the sphere which is above the xy plane. So this is half a sphere, and I have a cone which is z equals root x squared plus y squared, or phi equals pi over 4. So when I take just from the positive z axis, make a rotation of pi over 4. So this is pi over 4. I will get this cone. What is my solid? The solid is inside the sphere, below, above the xy plane, and below the cone, So it is not inside; it is below it. So the solid will be this part. Everything be below the cone. So this is a cone. Everything below it and above the xy plane. So this is the solid above the xy plane and below the cone. Now we go to describe D, the limits of rho, phi, and theta. So D now in spherical coordinate, it is the set of all rho, theta, and phi. What are the limits of rho? And what are the limits of theta and the limits of phi? And we go one by one. For rho, as we said before, we start from the origin. We take a ray starting from the origin and enter the solid. And we see where we enter the solid and where we leave the solid. So if I start from array from the origin, so this is the origin, we'll take array from the origin inside the solid. So the solid is here, not inside the cone, this is below the cone. So this is the array. Okay. So if I take this row, I really enter the solid at the origin. This is the origin. So this is my limit. And leave the solid at this curve, which is rho equals 2. This is rho equals 2. So up to rho equals 2. From 0 to from 0 to 2. Take a ray starting from the origin. Well, you enter the solid through the origin O, and you leave through rho equals 2. So this is my lower and this is my upper. 0, 2, 0, 2, 2. Okay. So this is for the rho. Okay. For phi, well, it is the angle, the points, the angle of the points. But these angles, we measure them from the positive z-axis, Any point in the solid, the points of the solid, what are the possible values of phi? Well, if you just take here, from here, from the positive z-axis to the cone, this is pi over 4. None of the points are inside the cone. So none of these values, 0 to pi over 4, will be part of the range of theta. But I will enter the solid at pi over 4. Until the xy plane. So the points in the solid have the following range of theta. Pi over 4 to the xy plane. The points on the xy. What is the value of phi on the xy plane? It is pi over 2. So it goes from pi over 4 to pi over 2. Any points in this part below the cone will have phi from pi over 4 to pi over 2. Pi over 2 is the value of theta for any point in the xy plane. So these are the limits of phi. What about theta? Well, theta, just notice the theta, we measure it from along, rotating on the xy plane, starting from the positive x-axis. Now, the solid is on the xy plane, and it is on the full xy, in the full xy plane, just inside the sphere, but on the full xy plane, in all quadrants. It is not only in the first quadrant, or just the first answer. It is in the 4 quadrants of the xy plane. What are the possible values of theta in that case? Well, it will go from 0 to pi over 4. 0 to pi over 2 pi. Okay. So you have a full cycle. Okay, from the positive x-axis. So it goes from 0 to 2 pi. The solid is on the full xy plane, inside the sphere, but on the xy plane. It lies on the 4 quadrants in the xy plane. So the possible values of theta are 0 to 2 pi. Okay. So this is the description of the solid. Now we just substitute in the formula. It becomes, we have to have the following. So now the volume, triple integral of 1 dv, it is the spherical factor, it is rho squared sine phi, with the usual order d rho, d theta, d phi. The inner goes with rho 0 to 2, 0 to 2. The middle theta 0 to 2 pi, and the outer phi pi over 4 to pi over 2. This is the setup of the triple integrals in spherical coordinates. Now we integrate in the usual way, starting from the inner with respect to rho. So this is sine phi is a constant. Integral of rho squared is 1/3 rho cubed, from rho equals 0 to rho equals 2. And we have the other two, pi over 4, pi over 2, 0 to 2 pi, d theta, d phi. When you substitute, we get 8 over 3 sine phi, d theta, d phi, 0 to pi over 4 to pi over 2. We integrate with respect to theta. Here theta, there is no theta, so sine phi 8. So this becomes integral pi over 4 to pi over 2, 8 over 3 sine phi. When you integrate with respect to theta, we get theta from theta equals 0 to theta equals 2 pi, and this is dv, and this is integral pi over 4 to pi over 2. This is 2 pi, it becomes 16 pi over 3 sine phi dv. Now we integrate sine phi, so this is 16 pi over 3, integral of sine phi minus cosine phi from pi over 4 to pi over 2. And this is minus 16 pi over 3. Cosine pi over 2 is 0, minus cosine pi over 4, 1 over root 2, So this becomes 16 pi over 3 root 2. Okay. So this is the answer. We consider now the following problem. Use spherical coordinates to evaluate the triple integral over d, where d is the solid within the sphere in the first octant only. So here we need just to evaluate using spherical coordinates. So we need to describe d in spherical coordinates, and we have the solid is inside the sphere, x squared plus y squared. X squared equals 9. It is a sphere of center, the origin, and radius 3. Just change it to spherical coordinate. This is rho squared equals 9, and hence rho equals 3, since rho has to be greater than or equal to 0. So we have this. D is the solid inside this sphere, but in the first octant only. So let's sketch this solid here. So we have a sphere, radius 3. Okay, so this is rho equals 3 in spherical coordinates. But this part is only in the first octant. So really I have only the part in the first octant. So everything above the first quadrant of the xy plane. So we have just part of the sphere in the first octant, everything above this first quadrant in the xy plane, x and y and z. So let's describe d in spherical coordinates. So d in spherical coordinates, rho, theta, and phi. So we need to find the limits of rho, and the limits of theta, and the limits of phi. For rho, we take a ray from the origin, and we check where we enter the solid and where we leave the solid. So if we take a ray from the origin, and in the first octant, okay, you enter the solid through the origin. You are already in the solid. So I enter through 0, the origin, and I leave through the sphere, whose equation is rho equals 3. So from 0 to 3. Take a ray from the origin. Well, I enter the solid through 0, the origin, and I leave through the sphere, whose equation is rho equals 3. So rho between 0 and 3. The limits or the possible values of phi, I have points in the first octant. And when you measure phi, you measure them from the positive z-axis. All points in the first octant. Well, on the positive x-axis, phi equal to 0. You continue until you reach the xy plane. Phi for the xy plane is pi over 2. So we'll go from 0 to pi over 2. Any point in the first octant, phi is between 0 and pi over 2. Pi over 2. For theta, well, it is in the first, the solid is in the first octant, and theta, you measure it as in polar coordinates. Any points in the first octant, the phi of that point will be from 0 to pi over 2. 0 to pi over 2 in the first quadrant of the xy plane. So it will be 0 to pi over 2. Or you can say, if I take the projection of the solid in the xy plane, the projection will be the first quadrant. The possible values of theta of the first quadrants, 0 to pi over 2. So this is the description of D in spherical coordinates. Now the integral here to evaluate it. So this is now the integral, the given integral. I have to use spherical coordinates, so I have to change also the function in spherical coordinates. When you change it, becomes 1/3. So this is in the triple integral. This is 1/3 rho squared. So this is x squared plus y squared plus z squared. It is rho squared. dv, the factor of dv, it is rho squared sine phi d rho d theta d dv. And now we set up the limits of integration for the inner row 0 to 3, and for theta 0 to pi over 2, and phi 0 to pi over 2, 0 to pi over 2. And then we start evaluating by integrating first the inner integral with respect to rho. So this is sine phi, so 1/3 sine phi. When we integrate rho power 4, it becomes 1/5 rho power 5, from rho equal to 0 to rho equals 3, and this becomes 3 power 5 over 3, 3 power 4 over 5 sine phi d theta d phi 0 pi over 2, 0 pi over 2. So this is the value of the inner integral. Now the middle one, or the next integral, is with respect to theta. This is constant with respect to theta. So this is 3 power 4 over 5 sine phi integral theta from theta equals 0 to theta equals pi over 2 d phi, and again 0 to pi over 2. This is for the second one, theta from 0 pi over 2. When you integrate, it becomes 3 power 4 times pi over 10 sine phi. So this is 0 to pi over 2, 0 to pi over 2 d phi. You integrate again, so this is 81 pi over 10 integral of sine minus cosine phi from 0 to pi over 2. And this is minus 81 pi over 10 cosine pi over 2, it is 0, minus cosine 0 equals 1, and this is just 81 pi over 10. So this is the value of the integral. Use the spherical coordinates to find the volume of the solid that lies inside the sphere rho equals 4 and above the plane z equals 2. So we have a sphere of radius 4 and we have a plane. So we need everything above the plane. Of course, for the volume solution, as usual, the formula for the volume is triple integral of 1 dv over the solid d And we need everything to be in spherical coordinates. So rho, the sphere is given in spherical coordinate. Z equals to the plane. We have to write this in spherical coordinate. So Z equals to, how to change the equation of this plane to spherical coordinates. In spherical coordinate, this is rho cosine phi equals 2, and hence we can just take rho equals to secant phi, secant phi. So the equation of the plane spherical coordinates is 2 secant phi. We need to describe the solid D in spherical coordinate. So as usual, the first step is just to try to sketch the solid D. And when we sketch, we have the following. We have a sphere of radius 4. So this is rho equals 4. And we have a plane, Z equals 2. This plane, its equation in spherical coordinate is 2 secant phi. And the solid is the part above the plane and inside the sphere. So the solid, our solid is this. Everything inside, but above the plane, above the plane. So it's just like a cab, okay, in our head. Okay. The part of our head above the cab, or inside the cab. So this is the solid. Okay. We need to describe it in spherical coordinates. So D equals the set of all points rho, theta, and phi. Limits of rho and limits of theta and possible values of phi. Okay. For rho, again we take array from the origin and we enter the solid. Where we enter is the lower and where we leave is the upper, the usual thing. So here, take array from the origin. So this is the origin here. You take array from the origin. The solid is the green part. We enter the solid through the plane. We enter the solid through the plane. What is rho of the plane? 2 secant phi. So this is the lower limit. 2 secant phi. 2 secant phi. Where we enter is the lower. So we enter the solid through the plane whose equation is rho equal to secant phi. So the lower limit of rho is 2 secant phi. And we leave it through the sphere. We leave the solid through the sphere. And the equation of the sphere is 4. So the upper limit is 4. This is the upper limit. So these are the limits of rho. 2 secant phi to 4. Next we go to phi. What are the limits of phi? Now this solid here, we measure phi from the positive z-axis. Well, and then just go until you reach the plane. Or really not exactly the plane, until you reach the point of intersection here and here. Until you reach the points of intersection. So points above the plane, where there is an intersection with the sphere. So what are the possible values? Of these phi? Clearly, the first point, the first possible value of phi is 0, because any points on the z-axis in this part is in the solid. So phi equal to 0. So this is phi equal to 0. This is the starting point. Until what? Where we really have a point of intersection. So at the point of intersection between the plane and the sphere, what is phi? That phi is the upper limit for phi. Where there is an intersection between the plane and the sphere. And of course, it is not a point. You have the intersection to be like a circle. So every point in that circle, what is phi? On that circle? So here, we have to find just the intersection between the two rows. Row plane and with row this. When you find the intersection, solve, you get 2, 4 equals. So just intersection here. You solve 4 equals 2 secant phi, 2 secant phi, and this implies cosine phi equals half, and cosine half will be phi equals pi over 3, pi over 3. So at any points where the plane and the sphere intersect, phi equals pi over 3. Okay? So the upper limits of phi is pi over 3. Pi over 3. Okay? So the points below the sphere and above this plane, phi will be from 0 to pi over 3. What about theta? Well, the solid, if we take the projection, it will be on the full xy plane inside the sphere. Okay, so it will take all points in the xy plane, okay, but inside the sphere. So the projection will be some circle here, and the projection for that circle, the possible values of that will be 0 to pi or 2 pi. Okay. Or we can say just take any point here. It is around the z. The solid is around the z-axis. So theta, for that, remember theta, we measure it from the positive z-axis, just like theta in the polar coordinates. And the possible values of theta for these points around the z-axis are 0 to 2 pi. A full circle. So this is 0 to 2 pi. So these are the range for the spherical description of the solid. With this description, we can just now substitute or just set up the limits and find the volume. So the volume, triple integral of 1 dv, we have rho squared sine phi d rho d theta d phi. The limits of rho 2 secant 2 4. The limits of theta, the middle one, 0 to 2 pi. The limits of phi, the outer, 0 to pi over 3. Now we integrate the inner with respect to phi, with respect to rho, sorry. So this is sine phi. 1/3 rho cube from rho equals 2 secant phi to rho equals 4. Okay, substitute. This is 1/3 sine. Let me just do it here, and then this is 1/3 sine phi. 4 cube. This is 64 minus 8 secant cube phi. 8 secant cube. So this is the integral. So now I have the following: 0. This equals 0 to pi over 3, 0 to 2 pi, and this is 1/3 sine phi times 64 minus 8 secant cubed phi d theta d phi. The next integral with respect to theta, again, it will be just because this is in terms of phi, so it will remain as it is. This is 1/3 sine phi, and this is 64 minus 8 secant cubed phi. When you integrate with respect to theta, I get theta from theta equals 0 to 2 pi, then d phi. This is 0 to pi over 3, and this equals integral 0 to pi over 3, 2 pi over 3 times everything. Okay, and I need to integrate it now, so I've just multiplied sine phi inside. So this is 64 sine phi minus 8 sine phi secant cubed phi. dV. Now I need to integrate this. So this is 2 pi over 3. So this is, take 2 pi over 3. Integral of sine هتكون cosine 64 cosine phi. Now how to integrate sine times secant to cube, sine times secant to cube. Well, we just take here, we take one secant هتكون sine phi secant phi times secant squared phi. Secant is 1 over tan, 1 over cosine. 1 over cosine, sine over cosine, tan. So this is tan phi secant squared phi. So really this is just sine phi secant cube because tan times secant squared. To integrate it, it is a simple u substitution. This is the function tan, its derivative is secant squared. So this is my u. When you integrate, you get minus 8. The integral of tan هتكون half tan squared phi. From 0 to pi over 3. To pi over 3. So this is the integral. Okay. So you integrate this. Now you substitute, and just now you have this, and substitute to get h the answer, and we leave this for you. We leave this for you. We consider the following problem. Use spherical coordinates to find the volume of the solid enclosed by the cone z equals root x squared plus y squared between the plane z equals 1 and z equals 3. So it is a volume problem, So the formula will be as usual, it's just triple integral of 1 dv over d. We need to find the solution in spherical coordinates, so we just change the given equation to spherical coordinates. So z equals root x squared plus y squared. To change it to spherical coordinates, substitute the value of z, x and y in terms of spherical coordinates. When we do that, it is not difficult to check that phi equals pi over 4. When z equals 1, the plane z equals 1, you get rho cosine phi equals 1, and hence rho equals secant phi, and also z equals 3. When you change it to spherical coordinates, you get rho cosine phi equals 3, and hence rho equals 3 secant phi. So now what is the solid? We need to find the limits for the triple integral. We need to describe D in spherical coordinates, and for that we need to sketch the solid. So we have the solid is inside the cone, which is phi equals pi over 4, and here this is h, the cone. Phi equals pi over 4. So this is the equation of the cone. Phi equals pi over 4. So you just measure an angle from the positive z-axis. You go an angle of pi over 4, and then just you rotate. So the angle from here to here, pi over 4. So this is the cone, and between the plane z equals 1 and z equals 3. If I take the plane z equals 1, and so the intersection between the plane and the cone will be this circle. So this circle will lies on the plane z equals 1, and its equation is rho, as we find it, this is rho equals secant phi, as we find it here. When you take the plane z equals 3, the intersection with the cone will be this circle. The equation of this plane z equals 3 and spherical coordinate, it is rho equals 3 secant phi. What is the solid? The solid is between the two planes inside the cone. cone. So everything inside the cone, between the two planes. Okay. So this is the solid. So this is our solid. The solid inside the cone, between the two planes, We need to describe the solid in spherical coordinates. So this is the set of all points, rho, theta, and phi. Rho between what and what, and theta between what and what, and phi again between what and what. For rho, as usual, we take a ray from the origin and we enter the solid, and where we enter the solid is the lower limit for rho, and where we leave the solid is the outer limit, upper limit. So we take a ray from the origin, so this is the origin, and take a ray. When you enter the solid through the plane z equals 1, and you leave the solid through the plane z equals 3. Okay. I enter through the lower plane and I leave through the lower plane. What is the equation of the lower plane? It is rho, it is secant phi. The equation of the upper plane is 3 secant phi. So these are the limits of rho. For phi, well, you are inside the cone, and the cone is pi over 4. So from the positive z-axis to phi pi over 4, all points, all angles are included. So all points will have phi between 0 and pi over 4. You are inside the cone, so it is just from 0 to pi over 4. What about theta? Well, you have, of course, if you take a projection, the projection will be a solid, a disk lying on the full xy plane. Well, just within some circles, of course. So it is really a full disk. So it is from 0 to pi, a full disk. Or any point. Notice the solid is around the positive z-axis. You will cover all possible angles of theta. One full cycle from 0 to 2 pi. So this is 0 to 2 pi. This is the description of the solid in terms of spherical coordinates. Next, just substitute in the formula. So the formula here, volume, triple integral, 1 dv حتكون rho squared sin phi d rho d theta and d phi. The limits of rho secant phi to 3 secant phi. The limits of theta 0 to pi, and the limits of phi 0 pi over. This is the setup of the limits of integration. The next step, we integrate the inner with respect to rho. So this is sin phi. Rho 1/3 rho cube, from rho equals secant phi to rho equals 3 secant phi. Substitute, this is 1/3 sin phi, 27 secant cube phi minus secant cube phi. And this is 26 over 3 sin phi secant cube. So this is the value of the inner integral. Okay, so this is the value of the inner integral. This becomes 0 to pi over 4, 0 to pi over 4, 0 to 2 pi. This is 26 over 3 sin phi secant cubed phi d theta d phi. For the second one, it is with respect to theta, and there is no theta in the integral here, so this is 26 over 3 sine phi secant cubed phi integral of theta هتكون theta from theta equals 0 to theta equals 2 pi, and this will give us just 2 pi. So this becomes 2 pi over 3 هتكون 52 over 3 pi sine phi secant cube phi d phi from 0 to pi over 4. Now we integrate with respect to phi. So this is a constant, so we need to integrate this one, and here to integrate this we take 1 secant, so this is sine phi secant phi times secant squared phi. Well, secant is 1 over cosine, sine over cosine tan, so this is just tan phi secant squared phi. Now to integrate this you can use a simple u substitution. If I let u equals to tan phi, the derivative is secant squared. So a simple u substitution, this gives us the following: 52 pi over 3. The integral here half tan squared phi from 0 to pi over 4. Okay. So this is 26 over 3 by 26 pi over 3 and 2 will 52 tan pi over 4 1 minus 0, tan 0 is 0, and this is 26 pi over 3. So this is the value of this integral and the volume of the given solid. We consider now the following problem. Write the triple integral in spherical coordinates. We have a triple integral in rectangular coordinates, and we need to write it in spherical coordinates or change it to a triple integral in spherical coordinates. And for that we have really first to describe the solid, what is the solid of the integral, then change it or then describe it in triple and in spherical coordinates. So what is the solid in this problem? So the solid here is the following. Here D, it is the set of all points, x, y, z, such that what are the limits of z and the limits of y and the limits of x, and we can read this from the limits of integration. So the inner one goes with z, correspond to the limits of z. So z goes between the root x squared y squared and root 8 minus x squared minus y squared. So these are the limits of z. What are the limits of y? The limits of y comes from the middle integral. So these are y between minus root 4 minus x squared to root 4 minus x squared. And the limits of x comes from the outer integral, x between minus 2 and 2. So this is the solid. Well, what is really this solid? We concentrate really on the z boundary, z limits, because the solid will be between two surfaces. What are these two surfaces? The first surface is z equals root x squared, so we have two surfaces here. The lower, which is z equals root x squared plus y squared, and the second one, which is the upper, it is z equals root 8 minus x squared minus y squared. So z lies between the two surfaces, or the graph of the two equations here. What is the graph of each one? Z equals root x squared plus y squared. This is a cone with the axis, with center the origin, or vertex the origin, and center and axis the z-axis. And the second one is a sphere, an upper half of a sphere. Okay. The upper half of a sphere of center the origin and radius root 8. So the solid or Z between a cone and an upper part of a sphere, an upper part of a sphere. So now we can sketch the solid here. So I have an upper part of a sphere. So this is the sphere here. So let me just write its equation. This is Z equals root 8 minus x squared minus y squared. And the cone Z equals root x squared plus y squared. So Z above the cone, below the sphere. Above the cone and below the sphere. So really my solid is this one. Everything in here, everything in here. Inside the cone and below the sphere. So this is my solid. Okay. If you go to the y and the x, now here y in the xy plane, so this is root 8, the radius of this sphere, root 8. Here in the xy plane, again it is the lower circle and upper circle, so I have a circle of center the origin and radius 2, so I have something like this. Okay, so this is 2, and this is 2. And x between minus 2 and 2, so really everything in this circle, in the xy plane. Really, this is the projection of the solid, in the xy plane. If we take the projection, we'll get the circle or the disk in the xy plane. Okay, so this is the projection. So this is the solid. Now I need to describe it in spherical coordinates, rho and theta and For that, we have to change the equation to spherical coordinates, and this is very simple to check that it is really phi equals pi over 4. And this is a sphere of radius root 8, square both sides and rearrange, change to spherical. You get rho equals root 8. So it is not difficult to find that. So the solid below the sphere, rho equals pi root 8, and above the cone, phi equals pi over 4. And we need to describe the solid in spherical coordinates. So what are the limits of rho? The limits of theta and the limits of phi. For rho, we take a ray from the origin and enter the solid, and where we enter the solid is the lower, and where we leave is the outer. So take the origin here. The solid is inside the cone, so I go inside the cone. So everything inside the cone. Of course, the solid also has some points inside. Okay, so the lower limit will be 0. I am entering the solid through 0. As long as I enter, I am at the origin. In fact, the origin is part of the solid. So this is the origin. You enter through the origin and leave through the sphere, which is root 8. This is the sphere. I enter within the cone. Everything inside the cone is part of the solid. So really, I enter at 0 and leave at the rho equals root 8. For phi, well, from the positive z-axis until I reach the boundary of the cone, okay, cool. All possible values from 0 to pi over 4. So from here to here, 0 to pi over 4. Any point in the cone, inside the cone, and below the sphere, the possible values are from 0 to pi over 4. Well, the pi over 4 is just the outer cone. So this is 0 to pi over 4. What about theta? Well, in fact, from the projection, if the projection is the full disk, this is the projection, the full disk, everything inside, then all possible values of theta are 0 to 2 pi. One cycle from 0 to 2 pi. So this is 0 to 2 pi. So these are the limits or the description in spherical coordinates. Now the given integral I, to change it to spherical coordinates, well, I have to change the integrand. This is rho squared power 3, it becomes rho cubed. So this is integral. This is rho power 6. This is rho squared power 3, rho power 6. And we have d rho, of course, dv. For dv, dz, dy, dx. This is dv, of course, in rectangular. So what is dv in spherical? What is dv in spherical? This is rho squared sine phi d rho d theta d phi. And now set up the limits of integration from the description here. For rho, the inner 0 to root 8. For theta, 0 to 2 pi. And for phi, it is 0 to pi over 4 pi. So this is the how to change the given triple integrals in rectangular coordinates to a triple integral in spherical coordinates.